Hello everyone, my name is Fatima Mihami. I'm a second-year PhD student at the University of Pau, Pays de la Dour in France. So in my PhD, I'm currently working on numerical modeling of free surface flows. So in this presentation, I will guide you through the development of a fast and robust shadow water model, which can be used for flood forecasting. As we all know, flooding is one of the most costly disasters in terms of both property damage and human casualties. This explains the constant endeavor to understand and manage floods and their impact. For this reason, many numerical models were developed to compute the evolution of flood hazards, and they have proven to be very reliable and cost-efficient. Most of these models rely on the solution of the shallow water equations. So in this presentation, I will show you how to build such models starting from scratch. In general, when developing a new numerical model, we are looking for a balance between two main properties. On one hand, accuracy, and on the other, computational cost. High accuracy means that the numerical results should be as close as possible to the exact solution. However, they should be at a low computational cost so it can be used for practical applications. As we all know, solving free surface flow problems requires solving the 3D Navier-Stokes equations combined with the free surface kinematic and dynamic boundary conditions. This can be very difficult to solve, especially for large-scale problems. So a simplification of the equations can be achieved by integrating over the water depth and thereby reducing the spatial dimensions from 3D to 2D. Nowadays, there exists many depth-integrated approaches, each based on different assumptions and approximations of the vertical structure. The simplest form of these depth-integrated equations is, of course, the shallow water equations, which were derived by Saint-Venant in the 19th century. These equations are based on the assumption that the pressure is hydrostatic and that the horizontal velocity is uniform over the water depth. Despite these strong assumptions, shallow water equations are still able to accurately model a wide range of problems where the pressure is nearly hydrostatic. Examples of these problems are river flow, tsunamis, dam break, and sedimentation. Moreover, shallow water equations can be seen as the foundation of many advanced depth integrated flow models. Boussy-Naskin-line hydrostatic models, for example, are based in essence on shallow water equations while including extra terms to account for the vertical variation and the dispersion. That's why, when developing an advanced free surface model, it is always a good idea to start with a shallow water model, which can always be extended. So solving the shallow water equations means that we need to compute the spatial and the temporal variations of three variables. We have the water depth h and the depth average velocities u and v. To do that, the domain is divided into small control volumes, each with the fixed values of h, u, and v. The shallow water equations are then solved at a discrete level for each volume. In the solution, the shallow water equations are divided into two main parts. We have the time derivation of the state variables and the numerical fluxes, which combines the convective acceleration and the source terms. This means that any changes in the state variables will depend on the numerical fluxes coming in and going out of the control volume. There exist many numerical techniques to solve the shallow water equations. In our case, we are using a staggered grid method. This method is based on the staggering of the variables. This means that the water height is computed at the cell center, whereas the depth average velocities are computed at the cell interface. The main advantage of this method is that it is very compact and lean and doesn't require complex computations, since the numerical fluxes can be computed with simple finite difference approximations. In the past, this method was mainly used for subcritical flow. However, with the combination of specific finite difference schemes, the staggered grid method is now applicable to supercritical flows and the flows including discontinuities. Beside the staggered grid method, our numerical model is based on a second-order time integration by using a predictor-corrector range CUDA method. It achieves second-order accuracy in space through a second-order upwind scheme combined with a mean mode slope limiter. The numerical scheme is explicit. This means that the time step is restricted by the CFL condition. The model is also able to account for battle friction through two formulations, the Manin-Strickler's formulation and the Darcy-Weisbach-Cheesy formulation. The numerical model is written in CUDA C++ and can be executed on graphic cards. We have chosen a GPU implementation because GPUs are optimized for highly parallel tasks through their architecture. They are equipped with thousands of cores and a very high memory bandwidth. This means that for problems without data dependency, such as it is the case for a shallow water problem, GPUs can support massive computation at a reasonable low cost. So this caters to fast computation and therefore could be used for real-time forecasting. In this slide, we present the model flowchart. As we can see, it is based on a heterogeneous structure which combines both the CPU and the GPU cards. In our case, the entire computation is executed on the GPU. The CPU only takes care of the initialization of the variables and of the saving of the output data. In order to assess the efficiency of GPU parallelization, we compare the computation time of two types of parallelization. The first one is the standard CPU parallelization with the 12-core CPU card, and the second one is the GPU parallelization with the 2048-core GPU card. For this comparison, we run the Gaussian drop test on both cards. As we can see from the graph, there is a huge gain in computation time from GPU parallelization. The GPU computations are around five times faster than the CPUs. Also, this which proves that the solution of the shallow water equations caters very well to the GPU parallelization. When developing any numerical model, it is necessary to check its accuracy. For simplified problems, the numerical solution can be compared with the analytical solution. This is the case for many standard shallow water benchmarking tests, such as the tests shown on the slide. However, for complex real-life problems, the numerical results are compared to either field or laboratory data. In this slide, we show some standard benchmarking tests where the model results are compared to the exact solution. Here we have some tests with the moving boundaries. For example, the idealized dam break over dry bed test case and the oscillation in a parabolic basin test. As we can see from the comparison figures, the model is able to accurately track the dry-wet transitions, which is important for inundation mapping. Also, we get very accurate results for a relatively very coarse mesh, which proves the non-diffusivity of the model. Since the shallow water equations are hyperbolic equations where discontinuities can form in the solution, it is necessary to verify the shock capturing property of our model. As we can see, the model provides robust and accurate solutions for problems including shocks. Also, when compared to other commonly used shock capturing numerical solutions, such as the HLLN scheme, the model is able to achieve similar accuracy, but with the advantage of much lower computation costs, since the numerical scheme we are using is not based on approximate Riemann solvers. In this section, we will test the applicability of the model to non-idealized problems, which include complex bathymetry. A commonly used test for shallow water codes is a dam break test. And since we are in France, we are using the Malpasset dam break. The man-passed dam break is also interesting since there is a field laboratory data available for 9 locations along the river valley, which can be used for comparison. The test case is computed with 20 by 20 meters grid size and run for 4,000 seconds. The arrival time and the maximum elevation results are compared with the existing data from the original event. As we can see from the figures, the model is able to achieve very good accuracy, and the results are the most realistic with the appropriate friction coefficient, which validates the friction implementation in the model. Also, the quality of the results from our model is comparable to well-known flooding models, such as Telemac 2D. The two models show similar trends in the differences between measured and computed solutions. So, to summarize, we have developed a robust and efficient numerical model for the solution of the shallow water equations. The fast computation of the model benefits from two key features. On one hand, the GPU parallelization, and on the other hand, the simplicity of the staggered grid scheme. The model has been validated with a variety of benchmarks and has proven to be very robust and applicable to many water flow problems. Also, the model as it is right now can be used as a flood forecasting tool, or it can be used as the foundation to an advanced dispersive water wave model. Thank you so much for your interest and your attention. If you would like more information or have any questions, please feel free to contact me by email. Thank you.